Okay, so we got cut off in the last video, so just getting us back together here. So this is that chip problem again, where there's 200 chips. The proportion of red is 100 out of the 200. So now we're drawing random samples of size 20. And as you can see, you can have different results each time from each sample. So in the first one, we had 8 out of 20 were red, then 11 out of 20, then 13 out of 20. And we take all of our SRSs and we put them together to create our sampling distribution. You can see that a lot of our sampling distributions are looking to be a normal approximation. But the idea that you have variability from one sample to the next is called our sampling variability. So there is variability that we will expect to see from one sample to another. It is sometimes called sampling error, but sampling variability is a much better term. So we describe the variability of a statistic by the spread of its sampling distribution. Okay, so now I want to start to talk about bias and unbiased estimators, but more I'm talking about what estimators would be okay to draw certain conclusions with the sampling distribution than others. So kind of a background to this would be a class is recording student heights in their class on a dot plot. So in the dot plot above here, so we're talking about they're finding the mean in a sample size of 4. So they have 4 students, they find the mean of their heights, and then they recorded it in a dot plot. In the dot plot below, I would assume that it is the same sample size. There are still 4 students in each sample, but they're clearly taking a lot more samples down here. So as you can see, both of them are centered around the actual mean. So the population mean was 66.07 in the one above. After taking a few samples, well, more than a few, but not too many, it was pretty close together. The center, it was still centered on the true value, on the true population mean. If you see the one below, it's actually even closer. It's more accurate the more samples that they took. The population mean was 66.07. The sample distribution shows a mean of 66.15. So they're both centered around the actual population mean. If you take a look what happens with the range, it's a very different story. So now you're talking about taking a range of 4 students in the sample, okay? But a range is found from taking your maximum, subtracting your minimum. There's only one true range, so you're never going to get that. If you're always drawing different heights, different highs and lows, different maximums and minimums, you're never going to get your actual range. So when you look at this, your population range is 21, where your center here is at 10.12. So your range is not centered at the true value. So we would call our mean, because it is centered on your true value, a unbiased estimator, where your range, because it is not centered at your true value, an unbiased estimator. So a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Parameter, guys, that is referring to your population. So I think that it's worth saying that we're not going to trust all of our estimators in a sampling distribution. We will we won't be able to trust maximums or minimums or ranges in a sampling distribution, but we will be able to trust proportions and means, because they will always be centered at your true value. And so they can be trusted, but we do have to check certain conditions first. But as long as certain conditions are met, then we will be able to use our sampling distributions to draw conclusions about our population proportions and means. But we'll talk about conditions in another video, not this one. Okay, so the lower the variability, the better your sampling distribution will be. So the variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. So the larger samples will give a smaller spread. The spread of the sampling distribution does not depend on the size of the population, as long as the population is at least 10 times larger than the sample. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. Parameter being the population. So, this is kind of showing your ideal situation. So we can think of the true value of the population parameter as a bullseye on a target, and of the sample statistic as an arrow fired at the target. So both bias and variability will describe what happens when we take many shots at the target. Okay, so an ideal situation would be an unbiased estimator, so no bias and low variability. So bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give similar results. And the lesson about center and spread is clear. Given a choice of statistics to estimate an unknown parameter, choose one with no or low bias and minimum variability. So we're going to start talking more specifics on two estimators. We'll start with proportions in the next video.